Hello everyone. Today we are going to talk about CAN bus in automotive systems. We will explore why CAN bus is needed for automotive industry. We will also discuss about the CAN frame format, CAN data protection, and also how CAN communicates with each other or CAN nodes communicate with each other, and how CAN has a mechanism of error detection and error correction. So, a very brief about me. I'm an experienced professional having around 10 plus years of experience in an embedded industry. Currently, I'm working as a ST4 in Cisco R&D Bangalore. So let's get started. Before moving to Canvas in automotive industry, we will see how RT thread can help us in automotive industry. So RT thread provides full stack solutions for various automotive applications. Even you might be aware, like in most of the automotive system, we use either Android, Linux, and for any real-time control systems, we use some real-time operating system. So in that, we can also consider RT thread, and RT thread also has a strategic partnership with many of the leading chip suppliers like NXP, Infineon, TI, Xilinx, and also RT thread developed under some of the guidelines which we required for the automotive industry. So it is already certified for ISO 26262, also certified for EC 61508 and EN 50128. So if you want to build something interesting in automotive industry and you are looking for some artists, you can consider using RT Thread, which already providing a full stack solutions for the automotive vendors or the solutions. Okay, so we will move ahead and we will see the contents, what we will be discussing or what I will be talking about Canvas here. So we will discuss first why Canvas is required. Then we will discuss about the Canvas introduction, how it differs from I2C, SPI Canvas. Then we will discuss about the CAN frame format, then Canvas access or CAN data protection and how Canvas works. So we will also simulate that thing as well. Okay, so we will move ahead and go for why Canvas. So why Canvas? Before starting this, maybe I will discuss about few of the other communication protocols. Like I believe UART, SPI, I2C, everyone might be aware about or everyone have used it earlier. So many of the people think why we cannot use UART, I2C, and SPI instead of Canvas in automotive industry. So you might be aware, like if we are talking about any electric vehicle that consists of many of the ECUs. ECUs means electronic control unit, and those electronic control unit communicates with each other. So if I will take an example of any electric vehicle, it can have multiple ECUs. It can have more than 100 ECUs, and if you want all 100 ECUs to communicate with each other, what we can use? Can we use UART? Okay, so UART, like two devices will do the communication with each other, and also the speed is not that high in UART. Then I2C will come into the picture. In I2C also the range will come something around 100 kbps to several Mbps. Then people might think, okay, why cannot we use SPI communication? SPI is even faster than the CAN bus. So the thing is, we can use SPI, but If you are aware about the SPI communication, you might be aware in SPI we use four pins. One is serial clock, then MOSI will come into the picture, master out, slave in, then master in, slave out will come into the picture. And there is a fourth pin which known as a chip select. So if you have four device you want to communicate with the SPI communication, you will be having four chip select pin. So now we will take a scenario of the electric vehicle and we have 100 electronic control unit. We want to communicate with each other through SPI. We need 100 pins just for the SPI communication. So you can imagine how much cost it will increase if we want to do the communication with SPI. So okay, SPI we also cannot use, and CAN has some more functionality as well. So it has a robustness and reliability which is required for the automotive system. So in an automotive environment, like if there are hundreds of ECUs connected, it can often electrically noisy, or we don't want any communication which get lost in the middle. So robustness is crucial for any safety and the performance of the automotive system, and CAN provides that flexibility. Even CAN also has a multi-master communication protocol. So if we will compare with SPI or I2C, which are primarily designed for a single master scenario, CAN bus supports multiple master devices and offer multi-master communication. So that is also one of the advantage. Then higher data speed, we already discussed it. SPI has more uh, faster than the Canvas, but if we will compare with the UART and I2C, Canvas is the fastest. Then network scalability. So Canvas can connect up to a large number of devices and it can do the communication with each other. Like there are some limitation there in for I2C, SPI also, like if you have a less number of pin, you cannot communicate with so many devices, but can provides you that flexibility. Then one and the most important thing, it has a error detection and correction mechanism. So this we will see in the next slide how can handle error handling and do the error correction and detection mechanism. So in summary, CAN bus is preferred in automotive application due to its robustness and ability to support multiple master. It also offers high-speed data transfer. Even it has advanced error handling capabilities as well. So if we will compare with all other communication protocol, it has so many advantages and these things. That's why CAN is needed for the automotive applications. Okay, so let's move ahead in the next slide and we will see, okay, what are the layers we have in the CAN bus communication protocol. So I believe everyone is aware about the ISO and the OSI model, and we have a SAML layer in OSI model, but in real life scenario, we never use all SAML layers. Even the real life implementation of the OSI model is a TCP IP model, and in that also the layers are less. Okay. So if we will talk about the canvas, we have a three-layer model. So we have a physical layer, we have a data link layer, we have an application layer. So data link layer and the physical layer are the two lowermost layer which mostly used for the serial data communication. So if so many devices are communicating with each other, those physical and data link layer will be connected with some cables and wire. We will see that later. So these you can think of the bus node. Bus node, you can imagine this is a one electronic control unit. Let's take an example. This is a BMS system, battery management system, and maybe this is a FOTA system, another thing which you are seeing. And if they want to do the communication, those physical layer will be connected with some cable. So we will see that later. But okay, we can see that this is a three-layer model, and mostly physical layer, data link layer, and application layer will come into the picture for Canvas. So, okay, CAD is developed by Bosch and has been standardized in 1993. It is also available as an ISO standard, and if you want to look, you can look for ISO 11898. First thing is a event-driven communication protocol. So Canvas works as a event-driven, and we will see that. And also here they have mentioned two variants, like high-speed variants and the low-speed variant as well. So high-speed variants, you can achieve the data rate up to 1 megabits per second, and in low-speed variant, the data rates can be up to 125 kilobits per second. And actually, it also depends on so many other factors like what is the distance between two nodes and how many nodes are connected. These all things will come into the picture when we talk about the data rate speed. But CAD has two variant, low speed and high speed variant. Okay, so let's move on next slide. And here we will see, okay, uh, how CAN network. So CAN network is a system made of CAN nodes. CAN nodes are electronic control unit. So in electric vehicle, we will be having so many electronic control unit. We will be having a dashboard ECU. We will be having a BMS system ECU. We will be having a FOTA system, if firmware over the air system ECU. We might be having a different ECU for a braking system. For um, for a infotainment system, we will be having another ECU. So there are so many ECUs which will be present in an electric vehicle, and that can be denoted as a CAN node. So each ECU you can think of a CAN node which exchange data with one another over their individual CAN interface. Now, CAN controller provides a uniform handling of the CAN communication protocol. So there are two things which is required if you want to do the communication, CAN communication. So CAN controller is required. So if you want to check whether your microcontroller unit which you want to use or the board which you want to use has a support of Canvas, you can see that it should have a CAN controller and it should have a CAN transceiver. So if you have both two in your uh, development board, then you can implement CAN bus. And how the wiring would be, so it if two nodes will be connected with the twisted pair line, we will see that in our next slide. So those, there would be two wires and two wires will be twisted, and these two wires will be connected to the all ECUs. So if we want to do the communication with the CAN bus, we just need two wires. So you can think about there is less complexity as compared to the SPI communication. SPI is required, SPI pins required based on how many devices you want to communicate with, because you need individual chip select pin for each device. But it can be a scenario, even if you want to communicate with hundreds of the ECUs, you just need two twisted pair wire. Through that, you can do the communication. So it is also cost effective. Okay, so this is the network design. You can think about this scan node as one of the ECUs. So you can think of three ECUs are there. One would be BMS system, one is infotainment, or one would be any, uh, we can imagine photo system. So if they want to do the communication, there are two twisted wires. You can see one is a CAN high and another is CAN low line. And these are the termination register. Okay. So only these two wires you need to connect with the CAN high and CAN low. And based on the voltage difference between the CAN high and the CAN low, it can determine whether the logic level is 0 or the logic level 1 is in the CAN bus. Okay. And as we have seen, this is a multi-master communication protocol. So uh, and also the priority is not based on the ECUs. Here in the canvas, the priority is based on the message. So this also we will see that later in the slide. So okay, so this is a CAN communication principle. You can think there are four nodes: CAN node A, CAN node B, CAN node C, CAN node D. And you can think about this communication matrix. So if this is ID, what you are seeing is 0 cross 1 2. These are the message ID. So let us suppose this is for break, 0 cross 1 2. Okay, and 0 cross 3 4 is for maybe door open close, or 0 cross 5 to maybe something related to infotainment or something like that. Okay, so here one thing you always remember: in canvas, the priority depends on the message ID, not based on the nodes. So the lower the ID, the higher the priority. Means if these are the message, you can think of 336 message are defined here from 0 cross 1 2 through 0 cross 3 A5. If let us suppose two message is trying to go into the CAN bus parallelly, let us suppose 0 cross 1 2 and 0 cross 3 4, then 0 cross 1 2 has a higher priority. It will send it first. Then after that, 0 cross 3 4 will be coming into the picture. Then it is also works as broadcast. So you can think, if we have sent 0 cross 1 2, uh, here it is mentioned like CAN node A is a sender and CAN node B is a receiver. But if anything has been sent on canvas, every node will receive that packet. So everyone will receive that packet, but through acceptance checking, CAN node C and CAN node D will drop that packet, and only CAN node B, which will work as a receiver, it will only accept the packet. So if you want to see this thing also, we can see that in with a visual thing here. So if I will run this, you can think about: can node is trying to send 0 cross 1 2. So okay, we will start it from scratch. Okay, so can node wants to transmit 0 cross 1 2. Okay, let them transmit. Okay, so it's just transmitted and everyone will receive. So every node which is in the canvas will receive that, but as can node we only require that packet. So acceptance checking will happen, and after that only can node B will accept it and rest of them will discard the packet. Okay, so this way the can communication happens. We'll move back to our slides. So the same way, let us suppose 0 cross 67. So 0 cross 67 will be sending by CAN node C, and as all are the receiver, so once CAN node C will send this 0 cross 67, everyone will receive it, and based on the acceptance checking, everyone will accept that packet. Okay, so let's move forward. This is a CAN bus level. So as we have discussed earlier, that logic 1 and logic 0, how it will define, because we have just only two wires, CAN high and CAN low, and it will be connected to the ECUs. So there are two types of CAN bus. So if you're using high speed CAN bus, the CAN high, when the CAN high voltage level is 3.5 volt and CAN low voltage level is 1.5 volt. So the difference between two would be 2 volt. So when it is 2 volt, it will be dominant, means the bit will be logic 0. And when the CAN high and CAN low both has a 2.5 volt, means the difference between the two will be 0, then it will seen or think as a logic 1. In the low speed CAN bus, it is little bit different. Like if we have a recessive, means logic 1, the CAN low will be on 5 volt and CAN high will be on 0 volt. And in the same here, The dominant bit you can think of, the CAN high is 3.6 and CAN low would be 1.4. So the difference between two would be 2.2 volt. So if the difference between two is 2.2 volt, it is treated as a dominant bit here. Okay. So, and these all things are mentioned in the ISO standard. So if you will look at the ISO standard 118982 or 118983, you will find the details for the high speed CAN bus and the low speed CAN bus. Okay, so now we will talk about the CAN data protection. So it has a twisted pair implementation. Why it has the twisted pair implementation? Because the electric vehicle can have electrical noise or some noise over there, and it can change something. So we use twisted pair and we use the difference between the voltage, so it will be used to reduce the noise and required for the reliable communication between the two. The same way we have a CAN termination, so the communication will happen that side. So we have a termination register, and both in you can see that RT, so it would be there, and in the mid all the nodes would be there. Okay, so now we will see about the logical error detection and the bit monitoring. So to detect corrupt messages, the CAN protocol defines 5 mechanisms. It has a bit monitoring, it has a stuff check, it has a form check, cyclic redundancy check, and the acknowledgement check. So in the bit monitoring, you will see the monitoring of the message format. So the monitoring of the bit coding of the step check or for acknowledgement check or the CRC check, these things happens in the CAN bus. So if you will see the CAN bus data frame, we have all the checks available over there. Okay, by that they will try to detect the logical error and will try to send acknowledgement based on it has a malfunction packet or not. We also check the stuff check. So this is a receiver task. So it compares the bit stream of a sequence of a 6 homogeneous bit. So it should not have the canvas, there should not be having a 6 homogeneous bits. So if you have a 6 homogeneous bits, you have to set one, or you have to set logic 0 between that. So this stuff checking is also needed. So if it is not happening, this will also a way they will check, okay, there is some error has been detected over there. Then the next thing which will come into the picture, that is form check. So form check serves to check the format of the canvas. So each can messages always has some format and also has some bit sequence at the certain position. Like they have a CRCD limiter, they have a acknowledgement limiter, they have a start of frame in starting, they have an end of frame at the end. So sender always transmit these message component recessively, and any format error, if receiver is trying to detect that, then this way it can detect the logical error inside the canvas communication. Then there is another logical error detection mechanism available in the canvas, that is a cyclic redundancy check. So the polynomial associated with the arriving data or remote frame should equal a multiple of a generator polynomial specified by a ISO 11898. So there is a polynomial is already specified in the ISO. You can look for it. And if this is not the case, then the data or the remote frame was corrupted during the transmission. So it will also check the cyclic redundancy check to make sure each of the bit has not been changed during transmission. So that is also one of the way a cyclic redundancy check will happen. Then there is a acknowledgement check. In that, when sender sends some task, and let us suppose receiver will not receive the task, the receiver will not send the acknowledgement check to the sender. And if the acknowledgement has not been received by the sender, or maybe if some malfunction packet has been received by the receiver, it will send the acknowledgement error. So then either sender will retransmit the packet, or whether whatever he wants to do, he will retransmit the whole packet again. So this type of logical error detection can happen in the CAN bus. Now we will talk about the error tracking mechanism. So CAN bus also has a error tracking mechanism. Let us suppose hardware reset happen. There are two parameters can always have, that is a TEC, transmit error counter, and there is also REC, receive error counter. And if the value of the TEC and the REC means the value of the transmit error counter or the receive error counter is less than 128, then the ECU will always be in error active condition. So let's take a scenario. We have hundreds of electronic control unit, and let us suppose one of the electronic control units is doing malfunctioning. It's sending some of the malfunction packet every time, and CAN bus is busy to handle those things. So what will happen? Other ECUs will not communicate with each other. So how we can resolve it? Either we can bus off that ECU which is doing the malfunction and which is disturbing the CAN bus communication. So for that reason, they have an error tracking mechanism. So each ECU has a transmit error counter and the receive error counter. So initially it will start from 0. Then let us suppose any transmit error happen. ECU will increase their transmit error counter, and in any error happen during receiving, it will increase the receive error counter. So if receive error counter and transmit error counter is less than 128, the node or the ECU will always be in an error active condition. Error active means it can transmit the packet, it can receive the packet. Then another cycle will come. Let us suppose a receive error counter gonna increase by 127. So it is more than 127, or the transmit error counter has increased to 127. So what will happen? That ECU or the device will go to the error passive section, and in that it can only receive the packets which is in the CAN bus, but it will not send any packet in the CAN bus until or unless the receive error counter or the transmit error counter will go down to less than 127. Now the thing is, let us suppose the transmit error counter will increase by 255 or more than that. Then what will happen? That ECU will get bus off. So it will not be the part of the CAN bus communication. And then what will happen? The ECU can do the software reset and will receive some receipt of 128 into 11 receive bit. Okay. So if the error counter has increased more than 255, the ECU node will be bus off and it will not be the part of the CAN bus communication protocol. So that is the whole agenda for the data protection in the CAN network. So it will track the error, and if any ECU is misbehaving, it will make it as a error passive. And if still it is misbehaving, it will go to bus off, software reset happen, and it can again join to Canvas. So this depends on the implementation, how you want to implement the whole thing. So that's all from my side. I can give more example for Canvas. So there is also a protocol, Lin protocol,